Okay, so we're going to be looking at 3D vectors now. The good thing about 3D vectors is that really vectors as a concept were never really intended to be just specifically 2D or 3D or even 4D. And a lot of the formulas or rules that we've used for 2D vectors are going to be really similar for 3D vectors, and it'll almost seem kind of natural or obvious how we extend them. The notation is largely the same. So I think the main way in which we want to address 3D vectors is to just take a few of the things we've learned in 2D and compare them to 3D. So that's one thing we're going to be doing. There are a couple of things which are unique to 3D vectors which don't make sense for 2D, but we'll look at those later. But then other than that, once you've learned about 3D vectors and how they work, you're mainly just going to be looking at solving slightly higher level problems where now things are working in 3 dimensions rather than 2. But all of the rules are largely the same. You know, things about scalars, the notation, all of that is basically the same. So this section, this lesson is mainly about just doing a few of the calculations we've done with 2D and just trying it out with now 3D. Just to get us started, I've got this puzzle that I quite like. I guess it does have a kind of real world application. If you ever need to package something that is outside the bounds of what you're normally allowed to package, if you want to carry very long narrow things on an aeroplane, then maybe this kind of technique can be useful. But it has an application in vectors, as we'll see in a moment. So have a think about this. You've got a long wooden stick. It's very thin, so it's mainly just the length I'm interested in. And if I want to fit that into a box, and these are the sort of Royal Mail limitations, for something to be a small parcel, the whole box must be 45 by 35 by 16. Don't worry about the weight. Given that these are my 3 dimensions for this cuboid, what is the longest stick that I can fit inside that box? And it's not 45, obviously. I can fit a longer stick than 45. Can you come up with the answer? What do you think? There's an exact number, and it is the correct answer. What is the longest stick that I can fit inside that small parcel? Have a think about it. You can pause. Okay, let's go to the next slide and I will just talk through this one. So just before I forget, our dimensions were 45, 35, 16. Okay, and let's just consider the 2D case just for a moment. Let's say instead of a 3D box, I just had a square, right? The longest sort of straight object that can fit inside that, or rather than square, rectangle, is something that goes along the diagonal, right? So that's our 2D case. So extending that to 3D, if I attempt to draw this sort of cuboid, so let's say that's 16, that's 45, and let's say that's 35 there. Okay, it doesn't actually matter sort of the order of the 3 lengths or the orientation of the box. That doesn't really matter. And then if I just sort of dash line what's going on the inside. Okay, there we go. So that's our cuboid. Then the longest length is going to be, or the longest stick that can fit inside goes from one corner to the diagonally opposite corner. Okay, so it's this line here I'm attempting to draw there. Okay, but how long is that line? We can work it out by using Pythagoras 2 times, right? So the first time we're going to use Pythagoras is to get, rather than those 2 red points, getting the line between them, let's consider this, let's say green, and this green one. Okay, how long is that green line? Well, that you should be able to do, right? Because this is 45, this is 35. So with a bit of Pythagoras, let's work that out. 45 squared plus 35 squared square rooted, and we get, let's actually write it in the third form. This will be 5 times the square root of 130, okay, by Pythagoras. And then now consider this other line here, okay, that one is 16, because that's the dimension of the box. And now notice that that red line is just the hypotenuse of the triangle which has these other two green lines as sides, right? Because this part here, that's a right angle. Okay, it's a triangle in 3 dimensions, but ultimately it exists in 3-dimensional space, but the triangle itself is still 2-dimensional. It has a right angle, you know 2 of the sides, so therefore the final length here is going to be Pythagoras again, do 16 squared plus 5 of square root of 130 squared, squared, and then square root the whole thing. Okay. Now, what you might notice is, rather than doing Pythagoras once and then a second time, if you consider what we actually did to get 5 root 130, there's a shortcut to this, and it's to literally do the following. Do 45 squared plus 35 squared plus 16 squared and square root it. And that will give you exactly the same answer as if you do this version here. In this case, then the answer should be, quickly work it out, 59.211. Oops, dot dot dot. Yeah. 59.21, good enough. Yeah, and that's it. That's the answer. That's the longest stick that can fit inside this particular box, which, if you consider, is actually quite a bit longer than 45, which is the maximum dimension. So it is a legitimate sort of life hack there. If you have something particularly long, which is technically not permitted to fit in the post or within a small parcel, if you just stuff it in the diagonal of a larger box, then you might be able to get away with it. So this does have an application to vectors. So let's have a look now at 3D vectors, and we'll see where this comes up. So what I'd like to do is effectively just compare a few different tools or equations or whatever we've got. What's the 2D version, what's the 3D version of various things. So first of all, let's talk about calculating magnitude. Distance between two vectors, unit vectors, and finally the a unit vector formula, which we use to turn any vector into a unit vector. Okay, so first of all, 2D. Oh, let's also note 2D in general looks like this, x, y. So let's say notation here. Or we can write it as x of I plus y of j. That tends to be how we notate it, or note it down. In 3D, you'll just write x, y, and then z. You'll just have a third number. So you'll have 3 numbers rather than 2 in a column. Fairly self-explanatory. And then instead of xij, you'll have xi plus yj. You will still have that, but you'll just add on a third. And it makes sense that this would be z. And what would be a natural choice for a third unit vector? I, j, k. Okay, we'll talk about k in a moment. But that's the notation for 3D and 2D vectors. In terms of calculating magnitude, the magnitude of xy, we already know. We said that's the square root of x squared plus y squared, which is the length of a vector using Pythagoras. And then this is where that postal problem comes in, the stick in the post box. We've just shown that the length of a line in 3D space, if you have its 3 separate dimensions, will just be the following: the square root of the sum of the squares of the components. So it's that simple. So if I had a vector that was, 2, 3, 5, I'd just do 2 squared plus 3 squared plus 5 squared and square root it. That's the magnitude. You can imagine for 4D vectors 5D, you can see how the pattern continues. Fortunately, we won't be doing those. Okay, and then the distance between two vectors. So let's say, how can we say this? So vector, let's say distance between two vectors, let's say A and B. So let's just write that here, A and B. For 2D vectors, you just do B minus A and find the magnitude, right? That we've done before. Or A minus B and find the magnitude, same thing. So the distance between two vectors in 2D is the difference and then the length of that difference. In 3D, and this is why this notation is useful, exactly the same. Just find the difference between the two vectors and take the magnitude. The only thing that's different is here, you'll be taking 2 components away from each other, and here you'll be taking 3 components away from each other. And then you'll find the magnitude using the method above. Okay, unit vectors. We had I and j, and in 2D we said I is the same thing as 1, 0, and j is the same thing as 0, 1. Okay. In the 3D context, this changes a little bit. Oh, by the way, I've just noticed I, j, and k up here. I put the line underneath rather than above. Let's just correct that. Okay, in 3D, it's going to be as follows. I will be still 1, 0, but now we're in 3 dimensions. So what should I put for the third component? Let's just stick with 0, right? Because there is no component in that direction for I. I keep putting the line underneath for some reason. And then for j, you could see quite naturally it follows, it's the same, it's 0, 1, and the third component is still 0. So what will k be? And again, it's quite intuitive, it's 0, 0, 1. Okay. Which makes sense, right? For 2D, you've got 2 vectors perpendicular, and for 3D, you've got 3 vectors in 3D space, and each of these vectors is perpendicular to the other 2, right? What you've effectively got here is, in 2D, you've got ij in 2 dimensions like that, whereas in 3 dimensions here, it's a bit small. You've kind of got ij in 2D and then k going upwards, and that's a 3D sort of image. This thing that I've drawn here is effectively the corner of a cuboid, right? And at a corner of a cuboid, you've got 3 lines coming out of that corner, and one of them is I, one of them is j, and the other is k. So it's sort of width, length, and depth. And then finally, the unit vector formula. So this was, in 2D, we said if you take a vector A and multiply it by 1 over its magnitude, then that gives me the unit vector in that direction. Right? It takes that vector A and it makes it shorter such that it's now exactly length 1. In 3D, the formula, you'll be happy to know, is exactly the same. Okay. Incidentally, I think I haven't used this notation. There's a way to refer to the unit vector of a vector, which is a hat. So literally take that vector and put a little hat on it, a little arrow up like that. That means unit vector. It means the unit vector version of another vector. Okay. Unit vectors really aren't that complicated. The notation just looks a bit weird. if you're not familiar with what all these lines are doing in this formula, but it's literally take a vector, divide it by its length, and you get the same vector but shorter or longer, so that it's length 1. That's all that means. Okay, so those are the key results. That's effectively a chapter in the book on 3D vectors there, 2D versus 3D. Now we just want to make sure we can definitely still use all this stuff. Let's do a few examples, and then you can do a few questions yourself. Okay, so let's do a couple of examples, and then I'll quickly mention the one thing that 3D vectors have that 2D vectors do not have. So these should be quite quick. We've got two coordinates, A and B. These are the coordinates, written horizontally, so they're coordinates rather than vectors at this point. Given that the distance from A to B is 3 units, find the possible values of k. Right. So what's the distance between two vectors? Let's call little a 503, and let's call little b 42k. Right, so now these are the position vectors, right? So in other words, OA is that, and OB is this. What's the distance between them? It's going to be b minus a, and then taking the magnitude. So what's that? That's 42k minus 503, taking the magnitude. So what's that? Combine that into one vector. 4 minus 5 is minus 1, 2 minus 0 is 2, k minus 3 is just k minus 3. Now find the magnitude of this vector. And the magnitude of that is the square root of minus 1 squared plus 2 squared plus k minus 3 squared. Let's go up here. So that's the square root of 1 plus 4 is 5 plus k minus 3 squared. Okay, and then that's the distance. What did they say it was equal to? It's 3 units. So this thing is equal to 3. So that implies if I square both sides, I get 5 plus k minus 3 squared equals 9. Therefore, taking 5 away from both sides, I get k minus 3 squared equals 4. That implies k minus 3 equals square root of both sides plus or minus 2. So k equals 3 plus or minus 2. My two possible values are 5 or 1. Okay, cool. All right, let's look at the next example. Okay, so this is going to be a reminder of how to use the scalar property or the scalar notation to talk about parallel vectors. We're just going to use it for 3D ones. So you've got two vectors A and B. There they are. First of all, find 4a plus b and 2a minus 3b. That's pretty simple. Just we're using exactly the same logic as before, which is when you multiply by a scalar, you're going to multiply the components, all components, by that scalar. And when you add two vectors, you're going to add all of the components again, add the x, add the y, and add the z. So we should get the following. So let's write that there. That's I is 12 minus 14, 20. See if you can beat me to b. Or I should say, sorry, not b, II. So you can beat me to II. 2a minus 3b. So I've got this, minus 3 lots of this. Okay, let's speed it up a bit. So that's 4 minus 12, minus 6 plus 6, 10 minus 0. So for I get minus 8, 0, and 10. Okay. Right, so then part B says state with a reason whether each of these vectors is parallel to 4i minus 5k. So one important point on this thing, 4i minus 5k, as a column vector, remember in 3D we've got I and j and k. So what does that actually look like as a column vector? It's 4, 0, 5. Right? It's not just 4, 5 or 4, 5, 0. Just remember that if the j is missing, then you've basically just got 0j. Right? Because there's a k here, we know we're talking 3D, so you have to just make sure that you acknowledge that there's a missing j. So it's 405. State with reason whether each of these vectors is parallel. Remember, parallel is the same thing as saying that one of them, call it A, not in this context, different A, different B. In fact, no, I'm not going to change it. A equals lambda B, or B equals lambda A. In other words, one of the vectors is a multiple of the other. Okay, this A and B that I'm rubbing out now, that had nothing to do with the A and B in the question. Just talking about two generic vectors. So any two vectors that multiply to make each other are parallel. Can we do that for any of these? It's very simple. Look at that 4. How do I get to 12? I multiply by 3. Is 0 times 3 also minus 14? Nope. So therefore not parallel. I don't even have to check the third component. So that one is not parallel. Then let's look at the other one. 4 compared to minus 8. To get from one to the other, I multiply by minus 2. 4 times minus 2 is minus 8. 0 times minus 2 is 0. 5 times minus 2, oh, that almost worked. Does that mean I've maybe made a mistake? Ah, yeah, sorry, this should be a minus 5. Oops, another mistake. Okay, so it's going to work now. That was suspiciously close. So 4 times minus 2 is minus 8. 0 times minus 2 is 0. Minus 5 times minus 2 is in fact 10. So yes, these two are in fact parallel. Okay. And of course, if you did it the other way around, this one times minus a half gives you that one. Okay, so parallel, it still works. It works exactly the same. Right, so now let's look at this one thing that annoyingly is a bit different about 3D vectors. Okay, so the thing that's different, if you remember for 2D, when we had a vector, let's say a position vector, we have this concept of an angle, right? There's an angle, and you can say what's the angle, the x-axis or y-axis, or what's the angle with respect to I or with respect to j. These are all meaningful questions. If you have a 3D vector and you say what's the angle of a 3D vector, I mean it's up to interpretation. It depends on what you mean. Do you mean with respect to I, in the direction I, or respect to j, or respect to k? So you do have to specify. In some sense, there's almost 3 angles to these 3D vectors, right? So let me just try and draw a sort of 3-dimensional axis. Okay, so this is 3D, and this is my x and my y and my z, and then it is a little hard to visualize because we're viewing a 3D situation on a 2D screen, right? So this is just an approximation of what's going on. You've kind of got 3 angles, right? You've got the angle it makes with the x-axis, which is that angle, right, which we'll call theta x. You've got the angle it makes with the y-axis, right, which is theta y, and then you've got this other angle which it makes with the z-axis, which is theta z. Okay, now this diagram is very confusing to look at, especially because it gives you this weird impression that somehow, you know, theta x, theta y, theta z, they're kind of segments of a single circle or segment of a circle, but this is 3 dimensions. It doesn't quite work that way. However, fortunately, I think at this stage you don't have to worry too much about this picture, although it would be nice if you can sort of visualize this in your head, that this vector has these 3 angles. What's important is that you know how to calculate each of these 3 quantities. Okay, unfortunately, this is one of those cases where you're going to be given a formula. You don't have to necessarily understand yet why it works or how, but you need to know what it means and how to use it. So it's this. If you have a vector, and let's write it this way, xi plus yj plus zk, then the angle theta x and theta y and theta z, to calculate them, we're going to use the following formula. Theta x will be such that if you take the cos of theta x, it will be equal to x over mod a. Okay? And then from there it doesn't get any more complicated. Y over mod a and z over mod a. Okay? Remember, this x here is just a number. It's the x component of the vector. That y, that z, they're just numbers, the y and z components. The mod a, also just a number. Just a reminder, we just defined it earlier. Mod a will be the square root of the sum of the squares. Right? So on the right hand side we'll just have a number, and then when you want to get theta x, for instance, you'll just do inverse cos of the number on the right hand side. Okay, and likewise with the other 3. So hopefully that makes sense. At least you know what these 3 angles represent visually. It's the angle, this one's the angle a vector makes with the x-axis, with the y-axis and with the z-axis. These are the formulas that will tell you how to get those 3 angles. It tends to be written this way rather than with cos inverse on the right hand side, just to remove any ambiguity, because sometimes you can be talking about an acute angle or an obtuse angle, but it won't be that complicated in your case. You can just do inverse cos of the number on the right hand side. Okay, so let me just quickly try this out to make sure we're doing it properly, and then finally you'll have some questions you can try. Okay, find the angles, the 3 angles, that the vector 2 minus 3 minus 1, let's just write it quickly that way, makes with each of the positive coordinate axes to 1 decimal place. In other words, find me theta x, theta y, theta z. Okay. So first things first, let's find the magnitude. It's 2 squared plus 3 squared plus 1 squared. I'm ignoring the minuses because I know they won't matter. So I get 4 plus 9 is 13, square root of 14. And then I know that theta x, in this case, I'm going to do cos inverse of something, likewise here, and for the x case it's 2 divided by the magnitude, for the y case it's minus 3, for the z case it's minus 1, and what do I divide by? It's root 14. Okay, and then we're basically done. So then you'll pop those in your calculator. I'm just reading them off the textbook. Make sure, of course, you're in degrees, not radians. And we should get the following numbers. Okay, so gone is this concept of talking about the direction of a 3D vector. Rather, we now talk about these 3 angles that it makes with the 3 axes. Cool. Right, one final example, a problem-solving one. Okay, so we've got 2 points, A and B, relative to a fixed origin O. Find the length, or find the vector, AB, and then show that OAB is isosceles. Okay. In this sort of instance, I think you don't have to worry about drawing a full 3D diagram. Rather, just imagine that your piece of paper is 3D space, and you can just draw your A and B however you like. What matters is that you're showing the relationships in the correct way. So this origin is 0, 0, 0, or as a 3D vector, let's write it as this, as a column. A is 4, 2, 7, and B is 3, 4, minus 1. Okay, this is not going to be some accurate diagram or a 2-scale diagram. The diagram is there to just put information on the page so that you can see relationships better between these points. Okay, AB is this thing. Let's maybe choose a different color. AB is that vector there. So actually, let's just do that first. Let's find AB, because we're then going to show that this thing is isosceles. So AB, if we go back to, remember the 2D logic, actually let's just put these other lines in here. Okay, we should know at this point that AB is the same thing as OB minus OA. Don't know why I've put magnitude there. Let's get rid of that. But just to remind you of the logic, it's the same as with 2D. A to B, is there an alternate path? Yes, there is. I can go from A to O, from O to B. A to O is the same as minus O to A, hence the minus O to A here. O to B is that O to B there. I add them together, and I get my A to B. Okay, so then A to B is O to B, which is 3, 4, minus 1, minus OA, which is going to be minus 4, 2, 7. So I get minus 1, 2, minus 8. Okay, so that AB there is minus 1, 2, minus 8. Again, I have no visual understanding of what's really going on in terms of, I can't see this line and visualize the 1, the 2, and the 8, but what I can do is understand that it represents that column vector there. Okay, show that OAB is isosceles. Right. What does that actually mean? For it to be isosceles, what do I need to actually show? Break it down into smaller parts. For it to be isosceles, all we need to do is show two sides have same length. That's it. Show two sides have the same length. So can we do that? Well, OA is 4, 2, 7, as we know. OB is 3, 4, minus 1. Thus, we now have all three vectors corresponding to the three sides, and therefore we can find their lengths, and therefore we can then compare if we have two that are the same. So you'll literally find magnitude of 4, 2, 7, magnitude of 3, 4, minus 1, and magnitude of, what was the other one? Minus 1, 2, minus 8. Okay. Sum of the squares, square rooted, and we end up with root 69, root 26, and 864, root 69. Okay, don't care what the actual values of those roots are, because we have it in third form, two sides, same length, and therefore that implies that the triangle OAB is isosceles. And that's it, done. Cool. So we can look at the questions now. It's mainly going to be a bit of calculation. it shouldn't be too bad early on because it is just the 2D stuff, but now you're using 3D vectors. You do want to practice the stuff with the 3D having an angle to the axes for sure, because that's new to you. But let's take a look. Okay, so 2 slides. There's 3 questions here, and there's 1 on the next slide. The 1 question on the next slide is a problem-solving style one. And those are the kinds of questions which everyone struggles with, I think. Or not everyone, but a lot of people struggle with. Once you get a problem-solving question with a vector, where it's like, here's a triangle, prove this, or can you show this particular property of a parallelogram, that's the stuff people find a bit difficult. Exam questions are rarely going to actually be just find the length of a vector or what's the angle it makes. Rather, you're going to use that information to solve a problem. So give yourself time to try that question on the next slide after you've tried the ones here. These 3 are just calculation questions. They're the fundamentals. What's the distance between 2 vectors? Can you find a unit vector? Can you find these angles? Once you've done these 3, checked your answers, you can then have a go at the problem solving question on the next slide. Okay, so pause now and you can try these 3. Okay, and finally you've got this question. Do note that in this case it might be worth drawing it out a little accurately, only because whenever you've got lots of zeros in a 3D vector, it is actually quite easy to draw it. 4, 2, 3 is hard to draw on a piece of paper, but 2, 0, 0 and 5, 0, 0, if I give you your sort of 3D axes, I personally think you should be able to picture those vectors quite easily. So then you can have a think about how you're going to work out the area of the triangle. Okay, don't just give up straight away. Try and think about using as many of the mathematical tools you've got and see how you do.